So now we discuss binary relations. Binary relations. And in this lecture we are going to prove that the class of all binary relations on a given set is actually a semigroup, forms a semigroup. So first we define binary relation. Okay. Let's define binary relation. If X is a non-empty set, then any subset of X is called a binary relation on X. Then any subset of X cross X, that Cartesian product, is called a binary relation on X. And there are some interesting relations. So that this phi empty set, it's always subset of X cross X. So this is a binary relation on X. And X cross X, it's also a subset of X cross X. So this is also a binary relation on X, and that relation is called the universal relation. Universal relation. And one more relation, which is this, which we denote by 1x. That is this relation, x comma x, with both the coordinates are same. X belongs to X. It's also a subset of X cross X. So it's also a relation on X. It's a subset of X cross X. And this relation is called a diagonal relation. So it's called a diagonal relation on X. So that's universal relation, that's diagonal relation on X. And if let rho be any relation, rho is a subset of X cross X. So that means then this rho is a set of ordered pairs actually, because X cross X is a set of ordered pairs with both entry is there in X. So rho is also a subset of X cross X. It's a set of ordered pairs. And if any ordered pair X comma Y, it belongs to rho, so that means X belongs to X, Y belongs to X actually. So X comma Y belongs to rho. Then we write it as, X is rho related to Y. So that's the notation. So whenever X comma Y belongs to rho, that means X and Y are related to each other under this relation rho, because rho is a subset of X cross X. It's a relation on X. And whenever this ordered pair it is in rho, then we write it as X rho related to Y. So that's the notation. So we don't use this notation. We use this notation. So now let's take the set of this collection of all binary relations on a given set X. So let Bx denotes the collection of all binary relations on X. Collection of all binary relations on X. All binary. So that means the phi is in Bx, identity relation is in Bx, because identity relation is a relation, binary relation on X, and that universal relation, it is also a relation on X. So that means the universal relation is also the member of Bx. It's a collection of all binary relations on X. So we'll try to define the binary operation on that collection. So let's take any two relations in this. Let rho comma sigma belongs to Bx. We define a binary operation. Define a binary operation O by rho O sigma, it's equal to, so it's a set of ordered pairs, it is a subset of x cross x, it should be subset of x cross x because we want to define a binary operation on Bx actually, so this should be the member of x cross x, so it is a set of ordered pairs x comma y in x cross x, it is a subset of x cross x such that there exists z in x, such that there exists z in x with x comma z belongs to the first relation rho and z comma y belongs to the second relation, this one. So that's a binary operation because it's clearly it's a subset of x cross x, it's a binary relation on x. Okay, so that means this belongs to rho comma sigma, it is in Bx, so it's a binary operation on Bx. Okay, so there are some properties of this binary operation. The first property is some properties. First property. If rho is subset of sigma, then this implies rho composition tau y, tau is a relation on x, it's a member of Bx, it is a subset of sigma composition tau, and it's on this side it's also true, tau composition sigma is subset of tau composition rho is subset of tau composition sigma. So whenever sigma is subset of rho, sigma and sigma, rho, tau, they are the members of Bx, their binary relation is on x. So if this binary relation is subset of, because binary there are actually sets, they are the subsets of x cross x, so whenever this is subset of rho, rho is subset of sigma, then sigma composition tau, it's again a binary relation that we have already seen. So it should be subset of sigma composition tau, and tau composition rho should be subset of tau composition sigma. So it's not difficult to verify these properties. So let's I verify this first property only. This one on that one. I'll verify this property here. So suppose rho is subset of sigma. We show that rho composition tau is subset of sigma composition tau. So let's choose any element here. So this is the set of ordered pairs. So let's choose any element. Let x comma y belongs to rho composition tau. Then by definition of the composition, so if whenever x comma y is in rho comma sigma, there should exist z in x such that the first order pair x comma z, it is in rho, and the second order pair z comma y, it is in sigma. So this is in rho composition sigma, then there exists z in x such that x comma z is in the first binary relation, and the second one z comma y, it is in the second. But this one, it is subset of sigma, so that means x comma z belongs to sigma and z comma y belongs to tau. So which implies that x comma y, it belongs to sigma composition, again by definition of the composition, because there is z such that x comma z is in sigma, z comma y is in tau, so that means x y is in sigma composition tau. So therefore this rho composition tau is subset of sigma composition tau. So this one, it follows on similar lines. So let's name this binary operation. Let's denote this by star. Okay, star. So next we try to show that this is forms a semi-group with respect to this binary operation star. theorem, Bx with this binary operation is a semigroup where that binary operation this is defined by star. So it's a binary operation. We just need we just try verify that this operation is associative. We show that binary operation O is associative. So for this we choose three elements. Let sigma rho comma tau belongs to Bx. We show that sigma composition rho composition tau is same as sigma composition rho composition tau. So let's choose element here because they are actually the sets. So let's choose element here. Let x comma y belongs to sigma composition rho sigma composition rho composition tau. Then by definition of composition, so we have two binary operations here. One is sigma composition rho, second is the tau. So again then there exists z in x such that x comma z belongs to sigma composition rho and z comma y belongs to tau. Now again here there exists again, because here it is against the composition, there exists u in x such that x comma u belongs to sigma and u comma z belongs to rho, and this one z comma y it belongs to tau. So this means this is if and only if actually this is if and only, you can see this if and only if x comma u belongs to sigma comma u comma z belongs to rho and z comma y belongs to tau. So let's join these two first. U comma z belongs to rho, z comma y belongs to tau. That means u, this first element and the last element of this one, this pair, u y belongs to rho composition tau. So this is true if and only if take this as it is, this one it's xu belongs to rho, so xu belongs to sigma and second. Now let's fill up these two with the help of the by means of a definition of the composition. So it's u comma y belongs to rho composition tau. U comma y belongs to rho composition tau. Now these are two binary relations, sigma, this is actually sigma here, first it's sigma. Now these two binary operations here, sigma and rho composition tau. So this means, and the second element and the first element of this, they are same. So it means that x comma y, it's if and only if x comma y belongs to sigma composition rho composition tau. So thus x comma y belongs to sigma composition rho composition tau if and only if x comma y belongs to sigma composition rho composition tau. So therefore sigma composition rho composition tau is equal to sigma composition rho composition tau. They are same. So therefore B x with this binary operation O is a semigroup, is a semigroup. It's a semigroup. And we use the following notation for sigma belongs to Bx. We compose sigma, we denote it by sigma square. It's also the member of Bx. And in, we have sigma q, it means sigma composition, sigma three times. So it's again in Bx. So in general we have sigma n, that means we compose sigma n times. That's simply X. So that's the notation or sigma square means sigma composition sigma. Okay. So let's now define this domain image of a relation, binary relation. So domain image, then we define converse of a relation. So if sigma is any relation in Vx, then what do we mean by domain? What's the domain of sigma? Domain of sigma means those elements in X such that there exists y in X with X comma y, they are related. It is in sigma. Okay. And what's image? Image of sigma. What's that? It's a set. It's y in X such that there exists X in X. Whether there exists X in X with X comma y. First, the second entry. That's the image. Belongs to sigma. Belongs to sigma. And one can easily verify that whenever we have sigma subset of rho, sigma is, suppose we have two relations, sigma and rho, sigma is subset of rho, this implies domain of sigma is subset of domain of rho, and image also satisfies the same. Image is the image of sigma is always subset of image of sigma is subset of image of rho. Okay. Let's illustrate this with the help of an example. So suppose X is say A, B, C. So let's take any relation on this. Let's take this sigma is equal to say it's a set of subsets. Suppose it's a set of subsets of the cross product. So suppose it's consisting of A, B, A, C. Sorry. It's a subset of okay, it's fine. It's subset of X cross X. It's a AB, AC. Let's choose say BC also. It's a subset of X cross X. Therefore, it's a relation. So, what's the domain here? Those elements of X such that there X to Y, X and Y are related. So, A is an element of X, then A is in domain of rho. A is in domain of rho if there exists some other element in Y such that the ordered pair belongs to that relation. Since for A there exists B, there are two elements actually for A, B and C such that AB belongs to rho, AC belongs to rho. So there are elements Y such that X comma Y belongs to rho here. So that means A is in the domain. Now let's look at B. For B we have C such that BC is in rho, so therefore B is also in domain. Now what about C? C is not in domain because for C there does not exist any element such that the order pair with first element C belongs to the relation rho. For C there is no ordered pair with first element C. So that means C is not in the domain. C is not in the domain. Now let's find its image. So image means the second entry of the relation. So that's B and C just. So domain is the first entry of the relation, first entries of the elements of the relation, and the image is the second entries of the elements of the relation. That's domain and image. And this you can easily verify this. Sigma is subset of rho, then domain of rho. This is an exercise for you. You can easily do it. It's not too difficult. It's not too difficult. It's not too difficult to verify this. So then we can see that this X row, the image X row, it's the set of elements Y and X such that X comma Y belongs to rho. So in this example, if I want to find the image of A, if I want to find for above example, so if I want to find a row, what's a row? What's a row? A row, the image of A, it's B and C. It has two images, B and C. So it's B and C. And what's image of B? What's image of B? That's C, just it's only C. And what's image of C? 0. Image of C. So C is not in the domain, so image of C is 5 set. It's not. It's empty set. It's empty set. So now you can say that X row is not equal to 5 if and only if X belongs to the domain of row. So because in this case A is in the domain, B is in the domain, but C is not in the domain. You can see here A is in the domain, B is in the domain. So therefore the image of A, image of the element A, it's a non-empty set. Image of the element B, it's a non-empty set. And C is not in the domain, so that's why the image of the image set of the element C is 5. And in case A row its coordinate is 1, then we denote A row by an element, by just an element, not by a set. For example, in this case B row is equal to C because its coordinate is 1. So in that case we denote it by just an element, not by a set. That's the notation. That's So next we define the converse of a relation. What's the converse of relation? So if row is a relation, then what's the row inverse? Row inverse means it's X. It's again a subset of X cross X. It's an element of X cross X such that Y comma X belongs to. It's just the reverse. So row inverse means if you want to find the row inverse of this relation, so here row, what's row inverse? Row inverse means BA, CA, CB. That's the row inverse. So row inverse means those elements X comma Y such that Y comma X belongs to row. Y comma X, that's row inverse. And you can easily verify that for any relation row inverse, whole inverse, it's equal to row. And for any say n relation is row 1 composition, row 2 composition, so 1 composition, row n inverse, it's equal to row n inverse, composition, row n minus 1 inverse, composition, row 1 inverse. That you need to prove the set inclusion. This one, it's a subset of that, and this is a subset of, and here this sigma inverse whole, it's a subset of X cross X. So you need to prove that this subset of X cross X it's a subset of row, and row is a subset of row inverse whole inverse. That's not too difficult. So you can easily do it. So these are some trivial things that you can easily do, so that you can easily verify those relations